Okay, we will now do the Chapter 12, Section 1 notes. And Chapter 12, Section 1 deals with what is known as linear regression inference. We're going to do a linear regression t-interval for the slope, and we are going to do a linear regression t-test with the slope. So it's all about the slope of the least squared regression line that we are going to be making inferences about. And let me explain to you, in essence, kind of the concepts behind this. Now, it's really important that you understand basic linear regression, which is Chapter 3, which the last video that I posted was on that. So you may need to go and watch that video just to make sure you understand the basics in regards to linear regression. But here is what we mean by linear regression inference. So what happens in linear regression is we want to see the relationship between two quantitative variables. So these quantitative variables could very well be, the explanatory variable, the x variable, could be the amount of fertilizer, and the response is the size of the tomatoes. Or the explanatory variables is the study time that students do, and the response variable is their score on a test. Or if this could be the amount of medicine, and this could be the cholesterol level, or whatever, but it has to be two quantitative variables. And so what's happening in inference is we are in essence viewing this, we are taking a sample. Like, let's say if we take a sample of 20 students, all right, and let's say this is the study time that they do in, let's say, hours, and this is their test score. We looked at an example like this the other day, and let's say there's a positive relationship amongst these 20 students. So we would plot those 20 points, and in this case we would look at those points and we would say, well, that is a positive relationship, and it is strong, and it is linear, and it appears to have no outliers, like we've talked about. And so we would create, in essence, the equation of a least squared regression line, as we've talked about. The line that minimizes the squares of the residuals, or the vertical distances there. And so we get an A and a B. We get y hat is equal to A plus BX, and we did all that in Chapter 3. But what we're going to do now is we're going to realize, well, wait a second. If we took another sample of size 20, and from the same population, and it was random and everything, so we get all these points, and we're expecting it to be a similar relationship, but it's not going to be exactly that. Maybe this one, y hat is equal to 61.2 plus 10.3x, let's say. We're not expecting to get that exact same thing with this another sample of size 20. It's going to be a slightly different line just because of sampling variability. So if we put it on this graph, it'd just be a little bit of a different slope and y-intercept. And then if we took a third sample and we came up with a third line, so maybe that's the first line, so maybe the second line was like, 59.6 plus 11.2x. If we came up with a third sample and we come up with a third line, it would also differ. And so what we're realizing here is this A and this B are actually estimates of population values. And these are just sample statistics. And in fact, this A is an estimate of the population y-intercept that we call alpha. It has nothing to do with the alpha significance level, but it is the y-intercept is if we did it for the whole population, whatever our whole population here, all the students, maybe all the students in our school system, all right, the thousands of them. If we did it for thousands of them, all right, then we could find what the parameter is, in essence, by doing a census. But also the thing that we're most interested in is we would realize this B is an estimate of what we call beta. Beta is the slope of the population least squared regression line. Not just of a sample, but if we did a census with the whole thing. So that is the concept of what we are doing. And so what we're going to do is we're going to make an interval around B. Okay, so we're going to take this. We want to estimate beta, and so we'll go B plus or minus our critical value times the standard error, just like every other confidence interval that we've done. And we'll say we're 95% confident that beta is in our interval. And then we will do a linear regression t-test using that is, in essence, our statistic. And so that's the concept of what you need to know before we do our examples. But the other thing is this. What happens when you have two variables that are totally unrelated? Like, let's say, for instance, if the explanatory variable was, let's say, someone's phone number, their cell phone number. All right, and then the response variable is, let's say, their score on a test. Two things that are obviously independent. In other words, someone's cell phone number has nothing to do with their score on a test. What will happen is that these points, in essence, are going to be going pretty much straight across like that, and that your least squared regression line is going to go like that. It'll be really close to zero. In essence, the beta is going to be equal to zero or really close to it. All right, and so that's what no relationship looks like. It doesn't matter if your cell phone number is this or your cell phone number is that. There's no relationship. So it will go straight across. And so that's what our null hypothesis is going to be, is that there's no relationship. And if there's no relationship, then the points are just going to look randomly scattered and pretty much go straight across. So if, for instance, if you're trying to figure out whether this medicine works, and so this is the amount of medicine. So here's the amount of medicine, and let's say we want to see its effect on people's bad cholesterol, the LDL. Well, if you graphed it, and you say here this person was given no medicine and this person was given like 100 milligrams and these people were given like 50 milligrams, if there's no relationship, you would look at it and you would say, well, it doesn't matter whether you get 0 milligrams or if you get 100 milligrams, and let's just say this is 10, let's say, your LDL is going to be somewhere around 10. These are independent, no relationship. So that's what no relationship looks like, is beta is equal to 0, and that's what our null hypothesis is going to be. All right, let's go ahead and look at we got two contexts that we are going to look at, and there's really two ways that the problems can be given to you. You have, as we've talked about, these computer printouts that you've got to be able to decipher. So that's important. That's probably the most popular way the data is going to be given to you. And the other way is they give you the raw data. In other words, they give you the actual points that you're going to put in list 1 and list 2, like we've done. So those are the two, types of problems that you have to know how to do. So let's look at this context. So this says, does how long a toddler sits at a lunch table help predict how much he or she will eat? A study was done with 20 toddlers, recording the time in minutes that they spend at the lunch table and how much food they eat in calories. The computer printout of the regression data shown below assume all conditions for inference are met, and so we won't have to do those in our first context. In our second context, we'll do, and those are pretty involved. We have the most involved assumptions or conditions in any of our inferences, actually. So number one, the first thing you got to be able to do is to create a 99% confidence interval for the slope of the true population least squared regression line. So that tells you we are estimating beta. Beta is the true population slope. B is the slope of the sample. So the slope, when you do it with these 20 toddlers, that's B. All right, so let's look at this. And so here's our computer printout right here. And so you've got, and as we've discussed in previous videos, you'd look at this and you'd immediately notice coefficient of constant. That's my constant in my linear equation, and that's A. That is my y-intercept, okay? This number that's right below that, that's B. That's my slope. That's the coefficient of my explanatory variable. The x variable, or the explanatory variable, is always there. These numbers that are next to A, they mean nothing to us. We'll never use those in this course. These numbers here are very useful. So, and most of the time these things will be given to you, but I'm going to show you how to find these in a second. But this is going to be a very important number. This is the standard error of the slope. That is the average amount that the slope would vary in repeated sampling. So there's S, the average of our residuals, or the standard deviation of our residuals. The average amount predictions will be off. There's R squared, the percent of the change in Y that can be explained by this model or can be explained by the change in X. R squared adjusted we'll never use. All right, so here we go. So to create a confidence interval, as we've done, you have to do the TAME acronym. You got to state the type of inference, verify your assumptions, do the mechanics, and then state your ending or your conclusion in context. So the type of inference, and so we got two types in this chapter, and they're on your calculator list, which I'm going to show you. So if you forget them, you can get them off there, but memorize this name. This is a linear regression T interval for beta. So linear regression T interval for beta, which we'll have to define beta, but we're going to define it in our ending anyway, so I'm not going to have you do it twice. And so that's all there is to it. All right. Our assumptions, we must verify our assumptions, which it says up here clearly, assume that all the conditions are met. So we will discuss those in essence in our next one. But for right now, we can just state it states these have been met. It's going to be a similar thing to sin. It's going to be sin, but make sure the data is linear. And then here's our mechanics. And so this is what, in essence, you've got to be able to do. Now, of course, on your formula sheet, it gives you your basic formula for a confidence interval, and that certainly still applies in this chapter. It is your statistic plus or minus your critical value times the standard deviation of your statistic. So that's what we'll do. Now, our statistic that we're interested in is B. So that's the big stat we're going to use in this chapter. Plus or minus our critical value is going to be T star. Of course, since we have a T star, we have to have degrees of freedom. And it's going to be n minus 2. We've got two variables we're working with, so you don't need to know why it's n minus 2 or really even essence what that means. You just need to know that it identifies which T distribution you're working with. So in this case, it's going to be 20 minus 18, 20 minus 2, which is 18. And then the standard error of the slope, which will always be given to you. So it's a relatively simple formula here, but that's how you do it. So B is there. So we have a negative relationship here. In other words, the more time they spend at the lunch table, the less calories they eat, evidently, in general. So B is negative 3.0771 plus or minus. Now we got to find our T star. Now it said they had 99% confidence. Of course, you can use your calculator for this, but we'll just use our table. So we go to table B, which is our T distribution critical values, and we would go to 99%. So there's 99%, and we will go up to 18 degrees of freedom. So 18 degrees of freedom is right there. So we go up this column, and it'll be 2.878. 2.878. So that would be 2.878 times the standard error. The standard error of the slope is this number. That is the average amount that the slope varies in repeated sampling. If we did many, many samples like this, okay, if we did many, many samples like this, that's the average amount that slope varies. That is the standard error. And so that would be 0.8498. There we go. And so this, when you do the arithmetic here, 771 plus or minus, that times that, of course, is our margin of error. So that's going to be 2.4461. So you could be asked about any of that. There's your standard error. You could be asked, what's the standard error? There it is. That's the same thing for a test, by the way, in this chapter. There's your margin of error. And then we'll go minus 3 minus that, which would be minus 5.5232, and then plus that, and that would give me minus 0.631001. And that's it. That's how you create your confidence interval. And then, of course, the ending, just like our endings before, we're just going to say we're 99% confident that this interval captures our parameter. But we have to say what our parameter is. And so you would say this: I am 99% confident. I am 99% confident that this interval, and it's right above what I'm stating, so I don't have to write it again, this interval captures our parameter, which is beta. Now you have to say what beta is. So beta, the slope of the true population least squared regression line of time at table, and number of calories consumed. Okay, and so that's how you make an interval. That's how they are That's how they are made. So, okay, let's go on to number 2. Number 2 says perform a test of the significance to see if there's evidence of a negative relationship between time at the table and number of calories. So we want to see, in essence, is there a relationship between two quantitative variables? Remember, in last chapter, in chapter 11, we wanted to see if there's a relationship between two categorical variables. All right. Well, now it's quantitative. It's a very similar sort of concept and reasoning going on. And so in this case, is there a negative relationship? They have whatever reason to believe going into the thing that there's a negative. Is the longer the kids sit at the table, the less calories they eat, which is sort of interesting to me. But I want to make a little bit more room here. So let's write out this. Of course, anytime you do a test, you have to do the THAME acronym. So we're doing our test. So in regards to number 2, you would say, okay, the type of inference, this is what is known as a linear regression t-test for beta. Like that, okay? And then, of course, we have our hypotheses. Similar to the chi-squared test of association independence, our null hypothesis is that there's no relationship. In other words, that beta is equal to 0. Is the line is just going straight across. In other words, it doesn't matter how much long they sit there, they're going to eat the same number of calories. That beta is equal to 0. And so what that is saying is there is no relationship. There is no relationship between time at table, and number of calories consumed. In essence, for toddlers like these, I think you could say. It doesn't say how the toddlers were selected. Were consumed. Number of calories consumed for toddlers like these, if you wanted to be complete there, which you need to be, for toddlers like these. Okay, there's no relationship. Now, the alternative is in essence that there is going to be a relationship, but what you notice here is that we're testing to see if there's a negative relationship. And so that's telling us what our alternative needs to be, is that beta is negative. And so, in other words, there is a negative relationship between the time at the table and the number of calories consumed for toddlers like these. And so that will always be, in essence, your null hypothesis is always going to be beta is equal to 0, no relationship. And the alternative is that there is a relationship. And of course, it's dependent. If it had said we want to test if it's positive, you go greater than. But if it just said difference, or if it just said we want to see if there is a relationship, then you would go with a two-sided test not equal to. And of course, then we have our assumptions, our THAME acronym. We have our assumptions, which is, we will do those thoroughly in the next example. But those have been met, It's said that they were met up there. All right, so now our mechanics. Okay, so our test statistic is going to be T. So we have a t-test statistic, and so anytime you have t or chi-squared, you got to state your degrees of freedom. Of course, we already know that's n minus 2, which is 18. And so our test statistic, let's look at our formula sheet. So on our formula sheet, the generic formula for a test statistic is this. It is statistic minus parameter over standard deviation of the statistic. And standard deviation statistic basically means standard error. We call it standard error because we're using estimates to estimate that. And so we call it the standard error. And so there's our formula. And so our statistic here is B. All right, our parameter is beta. Of course, we don't know it, so it's beta naught. And so in other words, it's 0 in essence in this chapter. And so that is in essence our estimated parameter. And then we have the standard error of the slope, which, like I said, will always be given to you. All right, frequently in a computer printout like this. And so our B, so looking up here, so our B is once again negative 3.0771. And this is just 0, all right? And so then the standard error off the table, 0.84 498. So in other words, and that's what this is. In this table, that t, that is our test statistic. It is always going to be equal to that divided by that. So that is how you find that question mark there. The t is always b over the standard error of b, in essence, because the parameter we're hypothesizing to be 0. And so in this case, when we find this value, it ends up being negative 3.621 when you find that value. And so in that table, if you wanted to fill in that table, this would be minus 3.621. All right, so there we go. Now that we know t, we can find our p-value. And so we have to, you could, in essence, estimate that with the table. I'm going to go ahead and show you how to use your calculator in that regard. And so what's happening here to find this p-value? So our p-value is, in essence, the area of the curve outside of that. In this case, lower than that, because it says less than. So in a t distribution, so there's my t distribution with degrees of freedom 18. So negative 3, as we know in a t and in a normal curve, is way out here. Okay, the p-value is that area, as we have discussed previously. And so here is negative 3.621. So to find that area, we're going to use TCDF. So we'll use TCDF from negative infinity to negative 3.621, and then you have to enter in your degrees of freedom, which is 18. So that's my lower bound. That's my upper bound. Okay, there's my degrees of freedom, 18. And so there we go. That would be, in essence, showing the work and that sort of thing. So I go second distribution, and I go down to TCDF right there. And I'm going negative infinity, or just put negative 9 billion or whatever, that'll work, to negative 3.621, 18 degrees of freedom. And I hit paste. There it is. And so we go. And so look how small a number that is. So that would be 9.769 times 10 to the negative fourth. Okay? So in other words, a really small number. That is our p-value. That is our p-value. Now, by the way, the p-value in this table is always going to be the two-sided p-value. So keep that in mind. So if you're given the table and you look at here to get your p-value, which in this is one, it's just going to be approximately 0 is what they're going to put there, by the way, in that table. But keep in mind, the p-value there is always for the two-sided test. So if you're doing a one-sided test like this, you would in essence have to divide it by 2, assuming that your estimate is actually less than in this case. And of course, then we do our p-value statement, which is just like all of our other p-value statements. You would say this p-value is this p-value is less than our alpha. We weren't given an alpha once again, so make sure and pay attention to what the given alpha is. But we weren't given an alpha, so we use 0.05 in its place, but it's less than any reasonable alpha value. So thus, I reject the null. The p-value is low, you reject the null, and then thus I have convincing evidence that, and then you restate the alternative in context. Okay, that there is a negative. There is a negative relationship. There is a negative relationship between, time at the table, and number of calories consumed for toddlers like these. Okay, that's how you do a linear regression t-test. So there appears to be a negative relationship. And so those are and most of the time, to be honest with you, this is the way that this problem is going to be given to you. That's how you do a linear regression t-interval and a linear regression t-test. All right, now the other thing. So our other context, well, I'm sorry, number 3. I need to address number 3. This is always a very popular problem when you're dealing with intervals and when you're dealing with hypothesis testing. So make the connection between the interval, the hypotheses, and the p-value. Now, you'll notice, and so the connection is in essence going to be this, all right, is the hypothesized value. Remember, the hypothesized value is 0. and it is not in the interval, that means in essence it should be rejected at the relative alpha value, which this is a 99% confidence interval. So since the hypothesized value is not in there, the p-value is going to be below 0.01 for a two-sided test. Well, this is a one-sided test, but it ended up being such a low p-value, but it would end up being below 0.005, actually, half of that, since it's a one-sided test. But so here's the connection that you need to be able to make, and we've done this before. All right, the 99% confidence interval does not contain the hypothesized value, which in essence is basically all the time going to be 0 in this chapter. The 99 does not contain 0, thus it should be rejected at alpha is equal to, now it would be 0.01, but it's half of that since it's a one-sided test. At alpha is equal to 0.005. So, thus, the p-value should be below 0.005, which it is. And so I've connected the interval with the hypothesized value with the p-value. That is an important concept. Okay. Now, and then the other way that this could be given to you, now let me just, and once again, as we have discussed previously, after we discussed in previous videos and in the classroom in regards to reviewing Chapter 3, it is very important to be able to state these things in context. The y-intercept, the slope, s, r, and r squared. Those things are asked about a lot. They're asked about more than actually all this other stuff we're talking about right now. So just, please, I've put other documents on Canvas. Certainly your book does a really good job of that, but please make sure that you can interpret all of those things in context. Those are, the most popular, questions in regards to linear regression. But here is, all right, so this is sort of the same, same type of problem. We're going to be asked to make a 99% confidence interval, perform a test, and make the connection, just like we just did. But this is the other way that this happens. In this case, they're given, they're giving you the data. And I'm not going to write out the whole mini essay because the mini essay is exactly the same thing. So I'm not going to write all of it out, but I am going to talk about the conditions because on the last problem we didn't have to do the conditions because it said the conditions were met. So I want to do the conditions or the assumptions. All right, so here we go, context 2. A company manager wishes to see if there's a relationship between the number of sales calls that his employees make in a day and the money from the sales made in that day in hundreds of dollars. You would certainly think that's going to be a positive relationship. The more calls they make, the more sales you would think they would make. Okay, he randomly selects 8 days, so there's a condition that's met, a random condition, and records the data below. And so there's our data, and it's obviously linear regression data because it's, first of all, it is quantitative, and this data is paired on 2 different variables. So anyway, create a 99% confidence interval for beta. So you would do the TAME acronym, the type of inference, linear regression, T-interval, and all right, so let me show you the assumptions. All right, our assumptions are going to spell out an acronym called LINER. All right, so of course, in previous inference we've done, we use the acronym SYN, and that really sort of applies here to SYN, but you have to make sure the data is linear. So that's the other way of looking at it. You could just say, well, I've got to SYN, I've got to make sure it's an SRS, an independent and normal, but I've also got to make sure the data is linear. But your book does the LINER acronym, which is another way of, in essence, looking at it, and I think it's a good way of looking at it. Look, this is very involved, and so frequently, a lot of times, they'll just go ahead and tell you, assume the conditions are met, or it may just be don't do any of the problem and just do the conditions. But so here are the conditions for linear regression inference. So it spells out the LINER acronym. Make sure the data is linear. Okay, how do you make sure data is linear? Just like we did in Chapter 3. Scatter plot, R value, residual plot. Make sure we have independence. In other words, that the values or the data isn't influencing each other in any way. The occurrence of one trial is in no way influencing the occurrence of another trial. In essence, we are going to check that our population size is at least 10 times our sample size, just like what we did before. Normality. Now, what we're going to check for normality, frequently it'll tell you to assume normality, and if it did, you would just say, hey, it said normality is met above, so it's met. But we just want to make sure the residuals, when you graph the histogram of the residuals, all right, there's no outliers or strong skewness. So that's what we're going to check there. Equal standard deviation, that just means when we look at our residual plot, is that for every value of x, the y values have a consistent variability. And we will talk about that. And then, of course, we always have randomness as a condition. Yeah, it has to say random or SRS, or random selection or random assignment to treatments in an experiment. That is always a condition, and it's always our most important condition. Okay, so with this data, let's see what we have. Let's see what we have going on here. So now, if you were to graph this data, so first of all, we're going to check linearity. And so to check linearity, just like what we did in Chapter 3, all right, you would graph a scatter plot, make sure to label it and scale it, find the R value using your linear regression command, and find the residual plot. And if you don't remember how to do that, watch the last video that I just made. And so you would look at this and you would say, well, there is a positive and linear and strong relationship between these two variables. R is very strong, and the residual plot is randomly scattered. It's got to have all three of those things. Because it has all three of those things, we have linearity is met. Okay, and so what you would state there in regards to that assumption, linearity is met because of the linear and strong scatter plot, strong R value, and randomly scattered residual plot. Independence is met because our population size is clearly bigger than 10 times our sample size, really. There surely is more than 80 days in the total population. Now, normality. Normality is going to be met because we don't have any outliers or strong skewness in our plot of residuals. If we took our residuals and we graphed them, so this is different than a residual plot. A residual plot is plotting the residual as it relates to the x variable. Okay, that's a residual plot. But in essence, your graph of the residual is just taking the numbers of the residuals, and you can make a histogram out of them. Here, there's only 8 numbers, and so I just made a dot plot. We just need to know that there's not any outliers or strong skewness, and there's no outliers or strong skewness, so we feel good about normality. Now, the next condition is equal variance or equal standard deviation. What we're going to do there is we're going to look at the residual plot. Now, when you look at the residual plot, all right, you'll notice, and with 8 points, it's really difficult to check this, honestly, but it needs, for every value of x, it needs to be going up and down sort of an equal amount. So a violation of that would be if your residuals really were tight to the line here, and then they got wider for bigger values of x. So that's not equal variance. It's really close there. It's really far away there. That would be a violation of that, in essence, of that condition. It needs to look like this. The residual plot needs to, in essence, have an equally amount up and down like that, have an equally random scatter. So, and then lastly, of course, randomness. As we've stated for all of our inferences, it's met because it says the days were randomly selected. There it is, the liner acronym. And I know that's a lot, but it is what it is. And so then in regards to our test, okay, all right, so that would be in essence the type of inference and the assumptions, and now the mechanics. All right, and so we'll use our calculator for this. All right, so to use our calculator, so what we'll do is we hit stat and edit, and in list 1, I put the number of calls, and in list 2, I put the response, which is the sales money. So this is what we'll do, is we'll hit stat, test, and we scroll all the way down pretty much to the bottom, past all this other stuff we've been doing. So, and there we go. So f and g, those are the two functions of 12.1, f and g. So this is a linear regression t interval for beta. So if you forget the name, you can look it up there. But you hit enter, so my X list is list 1, my Y list is list 2, frequency needs to say 1 or leave it blank. My level of confidence is 99%, so I hit 0.99. Store regression equation in Y1, and so if it didn't say anything there, so you go alpha F4 and hit like that, and there we go, like that, and so we go, and then we go calculate, and we got ourselves an interval. And so then we would say, so there's my interval. So in regards to number 1, so that is 0.05191 to 0.09502. And so our ending would be, we are 99% confident that beta is in this interval, or we're 99% confident that this interval captures beta, but then we say what beta is. The slope of the true population least squared regression line between number of calls and sales for this company. So that's how you do that. Now, and in regards to the test, now, and I can't help but notice whenever I make one of these intervals, the significance of the fact that 0 is not in the interval. Okay? 0 is not in the interval means it's to be rejected. In other words, there does appear to be a relationship between number of calls and sales. But so we're expecting a low p-value. How low? Well, if we do, this one's going to call us for us to do a positive relationship. In other words, our alternative is going to be greater than. So our p-value should be below 0.005. But anyway, all this stuff we did on the last example, but our null hypothesis is going to be that beta is always just beta is equal to 0, and in other words, there is no relationship, and say the two variables between number of calls and sales for this company. And the alternative is what we suspect might be true or what we're testing for, and that's greater than. Okay, because it says positive, significant positive relationship. And so the alternative there is a positive relationship, and then you can put ditto marks or whatever between number of calls and sales. All right, and of course you'd have the same liner acronym that's really involved, and I apologize for that, but I didn't make it up. All right, so anyway, so here's how we do our test. So we do stat, we do tests, and we scroll all the way down to linear regression t-test. So option F. So there we go, linear regression t-test. So list 1 and list 2, 1, positive, there we go, we hit that. And we get ourselves our t-test statistic, 12.6, certainly very dramatic. Our p-value is 7.52 times 10 to the negative 6. So, we would write t is equal to 12.6 for approximately. Of course, you always write your degrees of freedom, which is 6. It's the sample size minus 2. And then, of course, our p-value is equal to, in this case, 0.123455752. It'd be that. And that is going to be statistically significant for any reasonable value for alpha. And so you would say, just like we've done with our other tests, we are this p-value is below 0.05, thus I reject the null. Thus, we have convincing evidence that there is a positive relationship between number of calls and sales money for this company. So that's how you do the test. And then the connection with the interval and the hypothesized value is this p-value is telling us to reject the null. And the null is effectively 0, and 0 is not in the interval, meaning it's not a plausible value and should be rejected. And so there you go. That's section 12.1. I wish you much success in regards to 12.1. Thank you for watching this video.